Hello, my dear students, and welcome to the fourth and the final part for lecture number 1, semiconductor material. Actually, this is a very compact and very short part. It is it should be embedded in part number 3. However, due to some recording technical problem, we just split part number 3 into part number 3 and part number 4. In this part, we are going to terminate our lecture with what's called the drift diffusion model. We have already considered the drift model in lecture number in part number 3. Now, what I'm going to do is that I will briefly flash back on part number 3 and on the drift current, and then I will demonstrate the diffusion current. So let's now start sharing my presentation slides. I hope you can see my presentation slides now. Maybe there is a sharing problem, so let me make it another one. Okay. Okay, I think it's now working. So, generally speaking, we start first to define the scratch definition for an electrical current, saying that this electrical current is equal to dq by dt. And we said that Q is what's called the free carrier. Herein, free means that it's partially bounded or weakly bounded to the nucleus, and the carrier to demonstrate both electrons and holes. And the term d by dt is the term representing for the motion, for the guided motion. So you have to consider two main conditions in order to have an electrical current. First, to have a free carrier, and this has been already demonstrated either through the natural intrinsic concentration of the semiconductor material or by adding more electrons or more holes using the doping. And the second is this free carrier should move. In order to force carriers to move, we have two scenarios. The first is what's called the drift current. In the drift current, the process is very easy. First, this is a semiconductor. Let's assume that we have an electron hole pair generation. So we have an electron here in the conduction band. This is a free electron, of course, and this is a hole in the valency band. So what if we apply an electrical field? What if we apply a voltage source on this semiconductor? What we should expect that electron is a negatively charged particle. So electron should be attracted to the right-hand side where we have the positive terminal of the battery. And the hole is a positive charged particle. So hole should be attracted to the negative terminal of the battery. This is basically. So in order to demonstrate this attraction effect on the energy band diagram, we should make what's called the tilting effect. This tilting effect means that applying the minimum potential theory, my dear students, electron will start to act to go to this place because the potential energy of the electron here is lower than here. If you remember, we have mentioned in part number 2 that the electron energy increase upward. So this state has a higher potential energy with respect to this state. So electron will act to move to go to the lower potential state. Similarly, but on the counter direction will happen for the hole. From the hole perspective, energy increase by going downward. So this potential state is higher than this potential state. Accordingly, applying the minimum potential theory, hole will be attracted in this manner. Another important point, my dear students, if you remember, we mentioned that the sign for a thermodynamic equilibrium is to have a horizontal Fermi-Dirac. So whenever Fermi-Dirac level, I mean, of course, whenever we apply an electrical volt, that means that we are no longer in the thermodynamic equilibrium. Accordingly, this Fermi-Dirac should be tilted like this to indicate that this is an semiconductor under applied voltage. So this totally the process how drift current is applied. As you can see, drift current is equals to, if you remember in part number 3, we reached this general equation and we say that the electrical current J, sometimes we can call J drift because to indicate that this is a drift current, is directly proportional to eta, which is the electrical field. So whenever you have eta, you have a drift current. If in some problem in your exam or in your sheet, I didn't mention that there is an electrical field, that's totally mean that there is no drift current. So drift current appears only if there is an electrical field. And also there is some constant which is called sigma, which is a conductivity. This constant include, or not constant, actually it's a parameter. Sigma is not a constant. So it's a parameter. So we have a Q, which is a charge. Of course, this is a constant. N and P, and we already discussed how we can calculate N and P using the Fermi-Dirac distribution and the energy of states, and this mu N and mu B, which is the mobility for electrons and holes. And as also we previously mentioned, the mobility is inversely proportional to the mass. The fatter the body, the lower the mobility. And according to this, we have demonstrated that the mobility of electrons is much higher than the probability of holes due to the effective mass concept, if you remember from your material course. So this is generally how we can write an equation for the drift current, and you can somehow simplify this sigma term whenever you have an n-type material or a p-type material. Now, let's turn to the other side, or the other reason where we can have a carrier transport, which is the diffusion current. So now what we are going to show is what is the diffusion current, or how we can have a diffusion current. As I mentioned in the drift current is basically due to the electrical field. But what is the reason for a diffusion current? Okay, so to address the diffusion current, we have to return to our white paper and start doing some illustrative graphs. Let's make a mechanical example. If you have two water tanks, please accept my apologize as my drawing is very bad. So we have two water tanks, and there is a channel connecting these two water tanks, and also there is a valve where you can switch on or off. Here you have this level of water, and here you have this level of water. What happens if you open this valve? So I think it's an easy question. So water starts to diffuse from the higher level tank to the lower level tank, then till you have what's called a uniform distribution. So basically, any disturbance or any non-uniform distribution will result in a diffusion till a uniform distribution occurs. Another example, actually I'm demonstrating in my presentation slide. So let me return back to my presentation slide for a while. Another example is whenever you prepare a hot cup of tea, for example, maybe in the winter, what you are going to do is you are just put the tea packet in a hot water, and then you will start to recognize that the color of the hot water starts to turn from transparent, which is typically the water, to a reddish color, maybe to a dark red by the end of the day, or something like a brownish color. So what has happened? You have a medium where there is zero concentration of tea, which is the hot water, and you have a packet of tea particles, which is a very high density of tea particles. Whenever you insert the packet into the water, a diffusion process starts to happen between the high concentration region, which is the tea packet, and the low, or actually the zero concentration region, which is the hot water, till you have the full uniform distribution of the particle. So this is basically how diffusion currents happen now, or how diffusion in general happen. It's a general phenomenon. So in our case, if our carriers, I mean electrons or holes, are not uniformly distributed, what I mean is that you have a region where there is a huge number of carriers, and you have another region where there is a very few amount of carriers, then you should expect a diffusion current coming from the high concentration region to the low concentration region up till you reach a uniform concentration. But maybe the question will be now, why we should have a non-uniform distribution? If we remember our our electronics classes, we usually know that, for example, I told you that I have a silicon sample and we dope this silicon with 10 power 17 or whatever, and that's all. So it's a uniform. Why should we have a non-uniform distribution? Actually, there is two cases where you can have a non-uniform distribution. The first is to make it by force, what's called the non-uniform distribution doping, or what's called the doping profile. I mean, to intend to make your sample with different doping level. And this is basically the rare case. But the most common case, which is not included in this presentation, but it will be included in our module, is to have this non-uniform distribution due to junctions. To have this non-uniform distribution due to junctions. Let me try to illustrate it. This will be a very important part in our course later on when we go to devices. But let me make a very trivial example. So, okay. So, for example, if you make a PN junction, so P means that this is a P doped, which means that you have a huge number of holes, a low number of electrons. Versely, here you have a huge number of electrons, a very low number of holes. However, each of these samples are uniformly distributed, that's true, but at this border, you will find non-uniform distribution. Why? For example, if I would like to plot the number of holes across this junction, you will say that in this region, you have a very high amount of holes, and then suddenly the amount of holes will decrease to a minority carrier in the right-hand side. So in this border, you have a non-uniform distribution of carriers. Accordingly, you have to expect a diffusion current from here to here and from here to here or here to there with respect to the electrons. So this is one of the cases where, due to a junction and non-uniform distribution created. Back to our presentations. Okay, great. So now we know how we can have a non-uniform distribution. But what is the results? How we can calculate this current? So this is the diffusion current. Again, the diffusion current is due to non-uniform distribution of carriers. This is the key to have a distribution, a diffused current. So whenever we have a non-uniform distribution, as you can see, the flow starts to conduct from the higher concentration region to the lower concentration region. Accordingly, we can say that the diffusion current is proportional to dN by dx and dB by dx. I mean, whenever you have a non-uniform distribution, that means that dN by dx is not equals to 0 and dP by dx is not equal to 0, then you will have a diffusion current. But if I have a problem in your exam, I told you we have a silicon sample and the distribution in this, or the doping in this silicon sample is 10 power 18, then there is no distribution and no non-uniform distribution. So dN by dx is equal to 0 and dP by dx is equal to 0. And then there is no diffusion current. So the key for the drift current is the electrical field, and the key for the diffusion current is the dN by dx and the dB by dx. Here we have Q, which is of course represents the constant charge, and dN and dP are called the diffusion coefficients. We have electron diffusion coefficient and we have the hole diffusion coefficient. One interesting point about this equation is this negative sign. And this negative sign is a mathematical negative sign due to the slope. As the term dN by dx, as you can see, my dear students, or the dP by dx represents the slope. And knowing that usually, or in all the time, electrons are flowing from higher concentration region to lower concentration region, then as you can see here, the slope will be negative all the time. That's why we have the negative sign here and there to represent that this is a flow from high concentration region to the low concentration region. And in order to make sure that we are in a right manner, as you know, for electrons, this Q is a negative sign because the electrons are negative. So this equation, I'm sorry, here, this equation will turn to be positive because now I substitute Q with negative Q because electrons are negative particle. That's why this is turned to be a positive. However, this equation will be kept negative. So generally, this is the general drift diffusion model. As you can see, we have 4 elements representing the current. Let's first start to classify. Whenever you have eta, then this is a drift current. We have a drift current due to electrons, and we have drift current due to holes. But drift current is only occurs when there is an eta. If eta is equal to 0, then this term will not be in the equation as far as this term. The other 2 terms is the diffusion. One for electrons represented by dN by dx, and the other is dP by dx. That's why this one for electron, one for hole. Again, for hole we have a negative sign, but for electron we don't have this negative sign. This is another difference. And generally speaking, this is the overall equation. It's applicable to use this equation to demonstrate any type of electronic devices ever, knowing that its dimension is in the micrometer range or larger. Whenever the dimension is smaller than the one, or it's not actually a clear cut, but I mean, whenever the dimension is in the nanoscale, let me say it like that, whenever the dimension is in the nanoscale, then it is no longer valid to use this drift diffusion model, and we have to go to quantum modeling. But for conventional devices, whenever the models is relatively, or whenever the dimension is relatively large, then you can use the drift diffusion model freely. This is the most famous model used to demonstrate IV curves or JV curves in different electronic devices. We call this model as a semi-classical model. It's a classical model because we deal with electrons and holes as a particles. I mean, we use the mass, the velocities, the acceleration, displacement, and all this stuff. So the model is implemented based on Newton mechanics. That's why it's a classical model. However, we use some quantum effects, like the effect of mass, for example. These quantum effects are, and of course, the density of states whenever you are calculating N and P. Accordingly, we have a part of a quantum model. That's why we call it a semi-classical model. It's a transition model between the pure Newton mechanics model and the quantum models. A final important note regarding the relation between the drift current and the diffusion current, which is illustrated by what's called the Einstein coefficient. The coefficient for the drift current is a mu n and mu p, which is a mobility, and the coefficient for the diffusion current is dN and dP, which is the diffusion coefficient. Einstein have reached a mathematical information or a theory linking these two constants together, saying that dn over mu n equal kt over q and dp over mu p equal kt over q, which say that dn over mu n is equals to constant as far as you are working at a certain temperature, because K and Q are constant. So the only variable is temperature. So as far as you are working at a constant temperature, dN over mu n equals to dP over mu P equals to constant. By the way, this KT over Q at room temperature, generally this KT over Q is called thermal energy. And at room temperature, this KT over Q is equals to 25.9 milli electron volt approximately. So this is maybe the final part in our lecture, in our introduction lecture, let me say. Starting from the next lecture, we are going to demonstrate different devices, or we can say different applications, in order to understand and in order to apply what we already have learned with the drift diffusion model. This is the termination of lecture number 1, which is, as I mentioned previously, this is some sort of revision lecture, let me say like that. Now it's time to start practically our module. We will consider some of foundational devices, starting from a p-n junction, going to metal oxide semiconductor field effect transistor, and then we have the bipolar junction transistor, the tunneling field effect transistor, and the thin film transistor. In between, we will demonstrate also some important contacts that can be used for semiconductor physics and semiconductor devices. Thank you very much, and see you in the next lecture, inshallah.